About a deep learning model that I developed that is designed to do a range of facial growth related tasks. Synthetic aging, so predicting how a face will age. This has many applications, for example, in forensics, missing children's cases, is conditional shape generation. So our model will also be able to generate synthetic data conditioned on a specific age and sex of a person, which is mainly useful as a data augmentation technique. Then as a third application, kind of a byproduct of the model, we can also perform age estimation, sex classification. My data consists of over 5,000 3D facial scans, all taken with the 3DMD system. And we have a very wide age range, basically all ages, so 0 to 88 years. And also a smaller subsample of 60 individuals who also had a follow-up scan taken 6 years later, which we will use as a validation data set. The model I developed consists of 4 main training steps. Step 1, which is a conditional variational autoencoder. Whatever goes into this model has to be the same as whatever comes out. Step 2, take a person, we age it to a random different age, and we go back to the original age, and then we say, okay, this still has to be the same person. We borrowed some ideas from the GAN architecture, where we essentially use a second neural network, and then we want our model to output faces that it thinks are real. Also want the faces that we generate to actually be of the age that we specified for this person, to predict if it gets a face, what the age and sex of this person is. So first application is synthetic aging. We see some examples over here. So on the left, you see some real samples out of our data set. So they were encoded with their real age and then decoded with a bunch of different ages. And this way we can generate an aging trajectory for this person. Is how realistic are these predictions? Original image from each person. Then the next column is their actually aged image. Then we see our prediction and the error on. So overall, we had around an average error of just under 2 millimeters over the face. An additional experiment. We performed a simple identification experiment that at least we have a significant improvement of the identification rate after using this synthetic aging of the person. The model is also capable of generating completely new faces, which it hasn't seen before, and generate fully synthetic aging trajectories. So these are people that actually don't really exist and that our model has come up with. Also, like, is this what we generate biologically relevant? We did a small experiment where we generated a lot of faces for every age, and then we just simply took the average for men and women, and then the bottom row indicates the difference between the two. And here the colors indicate the blue indicates that the men's face is a bit more moved more inwards compared to the women, and the red means that the men's face is moved more outward compared to the women. Like the men have more prominent eyebrows, a bigger nose, all things we already know. But if in future studies we could include more of these populations and use that variable also in the model, we use this to generate specific growth trajectories for populations that have been ignored in a lot of clinical studies. A last application is age estimation. And we can repeat the exact same process if we wanted to do sex classification. So the age estimation results overall, you can see it on the graph on the left, and then the green is overall. We have around 2 years mean absolute error. For sex classification, we have a performance of just under 90%. But in conclusion, I showed that synthetic aging can improve facial identification performance. The model can generate new synthetic faces, and that this can be a useful tool for data augmentation. And then like my future dream would be adding more variables like maybe height, weight, BMI, ancestry, or even like people with certain genetic syndromes in the data set.